Okay, hello. Today, my name is Maya Walker, and today I'm going to be talking about dihedral groups and their properties and, um, like what tasks we completed about these groups, to help us, learn more about them and find out how they would be applicable to, what we're discussing with Professor Umar. Um, so a dihedral group. So what is a dihedral group? So a dihedral group um, is the symmetries of a regular polygon. A regular polygon is um, any shape that has the same length of sides. So, like an equilateral triangle or a square would be some examples of regular polygons. Um, and a dihedral group is a group that contains like a series of rotations and flips for this polygon. So it has like the properties of any other group closure, which means that if you performed a rotation and then a flip, it would still be in the group. So that combination would still be in the set of dihedral group, in that dihedral group. Sorry. Also, it has an identity element, which is just like the first one that we see here, which means that the F does not move at all. And then it has the inverse. So here we can see that if the F is rotated 180 degrees, if it's rotated the opposite way, 180 degrees, then that will be the inverse. We also established the size of a dihedral group, which is 2n, where n is the number of sides of the polygon. We proved this actually by showing that there were n ways of performing a rotation. So, for example, in a square, there would be four ways to perform a rotation before it went back to the original configuration that it was in. And then there are two ways to flip it. So this is like a flip, the reflection. So you flip it over once and then you flip it over again. So then you have two of that. So you have n ways to rotate it and two ways to flip it. And to get the order of that, the size of the group, you have to multiply the permutations. And so we multiplied 2 by n and got the size 2n. Then what was really important for us was to find out if it was abelian or not. We know that it is bad for the Uman's product property for a group to be abelian, and so we wanted to make sure this was not the case. So we did this by using the equation fh is equal to h inverse f. H inverse f, and so we assumed that this. So we established that f squared is equal to the identity and h to the power of n is equal to the identity. Then actually I have a visual of this. So I'm talking about this bottom part here. And so we get that, so we multiplied h on both sides. Actually, this was this way that you see on the left was a longer way of doing it. But the way that you see it on the right, at the bottom, would be the fastest way of doing it. So this would prove that identities And then the top one would prove that it's not abelian, where we find that if we can move H inverse past the F because it's commutative, then H would have to equal H inverse, which is not the case, so it cannot be abelian, which is good for us. Then there were some visualizations of this. The easiest for me would be the Rubik's Cube, because you can clearly rotate it one way and then have it rotate the other way. Another thing that Chris was talking about was a figure skater, where she could rotate 90 degrees, for example, and get back to her starting place after 4 turns, and then, or she could do a flip, I suppose, and get back upright, I guess, on after 2 flips. So these were 2 representations of that. So thank you.